Okay, so for FRK number 3, we have a uniform rod that is 2 meters long and has a mass of 4 kilograms. The rod is initially at rest at an angle of 60 degrees, and it will be released from rest, allowing it to rotate this or move this way, rotate this way. Now, there is a pin right here, so once released from rest, the rod will rotate about this point. And part A now wants us to calculate the initial energy of the system. Okay, so first of all, before starting the problem, I'm going to draw out the scenario because I know that I will have to determine the height of the rod before to be able to figure out part A. So here's a rod. Here are the labels of part A, B, and C that is drawn on a rod. Here's a pivot. And here is the horizontal. This angle is 60 degrees. And the length right here is given to be 2 meters. Okay, so I want to know the height of the rod about the center of mass. So basically the center of mass is right here, and the height will be determined by this length right here. Now I want to find this length, but I don't know what it is, but I do know that if the rod is split in half about this point right here, we would have this length right here, and that would be 1 meter. Basically half of this right here. This is L to half of L, so 1 meter right here. If I want to find this and this side right here, basically this thing forms a right triangle. So I can use trig to help me find my height. So I know that if I take the angle sine of 60, I get opposite, so 60 opposite is h over hypotenuse. Hypotenuse is this length over here, and that's 1 meter. I want to find my h and my height, so I'm going to times 1 meter this side. So h is going to be equal to sine of 60 degrees, which is 0.866 meters. So now I know my height. This is going to be helpful in helping me with the rest of the problems as well as part A. So as a reminder, part A wants me to calculate the initial energy of the system. So the total energy initial, I know, is equal to the initial potential energy of the rod. There is no KE because the rod is not moving initially, so it's just potential energy. I know that PE of the rod is equal to the mass of the rod times G times the height of the rod initially, HI. So now I'm plugging my numbers. Mass of the rod is, so mass is 4 kilograms. Mass is 4 kilograms. G is 9.8 meters per second squared. And height I just determined is 0.866 meters. Plug all this in a calculator, I get 33.948 joules as my total initial energy. Okay. Now part B asks me what is the angular acceleration of the rod at the instant it is released. Okay. So to find angular acceleration, I'm going to need to use torque. I know that torque is equal to the total force that's perpendicular to the moment of arm times R, and I also know that torque is equal to the moment of inertia of the rod times its angular acceleration alpha. Okay, so the total force that is perpendicular to the rod right here that's applied is Fg. It's Fg, and Fg is equal to mg. I also know that my moment of arm is, so if this is Fg, right? This is Fg. I know that my moment of arm will be this length right here, perpendicular to Fg and straight to the pivot. So it will be this length right here. This length right there, R right here, is essentially equal to L over 2 cosine theta. So basically the hypotenuse is L over 2 then times cosine of theta. And then I also know that the moment of inertia of the rod is equal to 1/3 ml squared, since the rod is pivoting at its end. That's why the coefficient is 1/3. Okay, so now I'm gonna sub all of this into this relationship right here. So total force is mg. R is L over 2 cosine of theta. Moment of inertia of the rod is 1/3 ml squared. Alpha remains alpha, because that's what we're trying to solve. Okay, so right now the m's cancel out. The l's, one of the l's will cancel out. So there's one L over here, and it will cancel with this L over here. And so if I want to isolate for alpha, I will have times 3 to this side and divide by L. So alpha is going to be equal to, so if I times 3 over, I will have a 3 in my numerator. I have a g right here and a cosine theta. And for my denominator, I have a 2 and divide L over, so I have an L as well. Now I'm going to plug in my numbers. G is 9.8 meters per second squared. Cosine of the angle is originally 60. And that's where I want to find my acceleration, or my angular acceleration, and my 2 and length is 2 meters. So plug all this in the calculator. 3.675 rads per second squared. That is my angular acceleration of the rod the instant it is released. Okay, now part C wants me to just to tell, once the rod is released and it rotates, does the net torque stays the same, increase or decrease, and justify why. Okay, so net torque. So first of all, I'm gonna start from the beginning. So as the rod rotates, I know that when the rod rotates right here, going down right here, the angle is gonna decrease. So theta decreases. As theta decreases, torque is going to decrease. I mean, torque is going to increase, because mathematically cosine of theta in the equation torque is equal to mg over 2 cosine theta. Basically this right here will increase. So to explain why it's this, so the angle decreases, but when the angle decreases, cosine of theta will increase. Cosine of theta is part of defining torque, and so if cosine of theta increases, torque will increase as well. There. Now part D. Part D wants me to rank from greatest to smallest, and it wants me to compare the angular acceleration of each of the different points on this rod. I mean, I know that all of them will be the same. So alpha A is going to be equal to alpha B is equal to alpha B and alpha C. All of them are going to be the same because angular acceleration is the same for all points of the same rod. Okay, part E. Part E wants me to compare the angular velocity. Once again, anything that's angular should still be the same if it's on the same rod, so that means omega A is equal to omega B plus is equal to omega C. And that's because angular velocity is the same for all points of the same rod. Okay, part F. Sorry, I don't know why my recording cut off again. Now for part F, it says to rank from greatest to least, comparing the acceleration tangential of each of the points on the rod, A, B, and C. Okay, so I know that the farther away from the pivot, the larger the R will be, and so the acceleration will be bigger because acceleration tangential is essentially equal to alpha times R. A bigger R means a bigger acceleration, obviously, so the farther away, the bigger the acceleration tangential the point will be. So that means A tan at point C is going to be greater than A tan at point B, which is greater than A tan at A. And the reason is because, as I said, A tan at any point on the rod is equal to the angular acceleration of the rod, which is the same throughout, times the radius or the length that is away from the pivot, or the R. And while alpha remains the same, so angular acceleration remains the same for each point, R changes or R varies. R is increasing from A to C, and R is and since R is in the numerator, that means a larger numerator means a larger number, thus A tan increases from A to C. Okay, essentially what I said is that A tan is equal to alpha times R. Alpha is the same, but R differs. R from A to C increases. That means A has the lowest R, B has the next lowest R, and C has the next greatest R. So since C has the greatest R, it will have the greatest A tan. Then comes B, then comes C, and then comes A. There. Okay. Part G now wants me to compare or rank the following from greatest to smallest, and this is the angular, no, not angular, the centripetal acceleration of each point on the rod. from A to C. Okay, so I know that the centripetal acceleration of C will be greater than the centripetal acceleration of B, which is greater than the centripetal acceleration of A, and here's why. And so this is because the centripetal acceleration equation is equal to v squared over r, right? And v squared over r is essentially the same as r times omega squared. Basically, if you sub in so v is equal to r omega. Now if you square r omega, you get r squared times omega squared. Then you can cancel out one r, and you have r omega AC is equal to r omega squared. Okay, so while omega remains the same throughout the rod, r varies. R is increasing from A to C. R is increasing from A to C, being in the numerator. An increase in R means a bigger centripetal acceleration, AC. That means AC increases from A to C. So essentially, this is the equation for centripetal acceleration, r times omega squared. Now this stays the same because that's established in part E. Omega stays the same throughout the rod for all points, but r it differs for each point. Now r is in the numerator, so if the bigger the r, the bigger the centripetal acceleration. So since C is farthest away, it will have a biggest r and biggest centripetal acceleration. Then comes B, then comes C, B, and then A there. My recording stopped again, and I found out that it was due to some storage issues on my phone. Anyways, for part H, we are asked to calculate the time it takes for the rod's position to be perfectly horizontal, basically when theta is equal to 0 degrees. Okay, so for this problem, it looks like I'm going to use calculus because I don't have any function that is related to time yet. Okay, so first of all, when doing calculus, I need to convert degrees into radians because working with degrees in calculus will cause some problems in math. So I'm going to convert 60 degrees into radians by times it by pi over 180. So this results into pi over 3, and that's radians. Basically 60 degrees is equal to pi over 3 radians. Okay, so now I'm going to use average angular acceleration to help me find time. Now I need to find average angular acceleration first, and here comes the calculus stuff. So average angular acceleration is going to be equal to, well, from theta is equal to pi over 3 to theta is equal to 0. Basically, from 60 degrees to 0, same thing. It's going to be equal to 1 over 0 minus pi over 3. Basically, these become the difference with this. This becomes the subtraction down here, and these also become my bounds. So pi over 3 to 0, and then theta with respect to alpha with respect to theta and d theta. So this is the equation for average angular acceleration. Now I have this equation, actually it's up here. I have alpha in terms of theta right here. So I'm going to use this equation. So this is going to be equal to 1 over 0 minus pi over 3, same balance, pi over 3 and 0. I'm going to substitute this equation in, so this thing in right here. So 3 times g, which is 9.8, those are constant, over 2 times L is also constant, which is 2 meters. And then I have cosine of theta, and then d theta. Okay. So these are constants, so I can bring them to the front. And basically this, all of this, and then divide by all of this and this times together makes negative 7.019. Wait, hold on, I'm gonna write it next line. Once again, this, all of this times this reduces down to negative 7.019. And then now I'm gonna integrate cosine of theta. Integrating cosine of theta is sine of theta. And then I have to plug in 0 and pi over 3 for theta right here. Okay, so basically what I had was equal to negative 7.019. Then plug in 0 and pi over 3 for theta, so 0 minus sine minus pi over 3. Basically, I plug these two in right here, and I get this. And then this reduces down to 6.078 rads per second squared. That is my average angular acceleration. Okay, now that I have this, I need to find my my final angular velocity, and I can do that using energy. So PE of rod initial is equal to KE rotational of rod final. Now I know from the beginning I've determined my energy PE rod initial is this 33.948. So 33.948 joules. And my KE rotational is equal to 1/2 times the moment of inertia of the cylinder. No, not cylinder. The rod, which is 1/3 times m. M is 4 kilograms times L. L is 2 meters and then squared. And then times omega squared. This is omega final, by the way. So I want to solve for omega final squared. All I have to do is divide this and then square root everything. Doing that, this is what I'm gonna have. So 33.948 times 2 times 3, then divide by 4, divide by 2 squared. So all of this results into, and then square root everything, all of this results into 3.568, and the units is rads per second. So this is my omega, or my final angular velocity. Okay, now that I have that, here comes the kinematic stuff. Okay, so this is the equation for average angular acceleration. Average angular acceleration is equal to my angular velocity final minus my angular velocity initial over time. This is the critical equation that is going to help me find time. So I found my average angular acceleration. It is, let's see, oops, it is this up here. So 6.078 rads per second squared is equal to my omega f, I found right here, is 3.568 rads per second, and my omega I know is 0, so this term cancels out because the rod is initially not rotating and over time. Okay, this will help me find time. So time multiply to this side and divide 6.078 to this side. So t is going to be equal to 3.568 over 6.078. Time finally is equal to 0.587 seconds. There. Now that's part H. Part I tells us to do the same thing, calculate the amount of time it takes for the rod to travel, but this time for the second half of its total angular displacement, so from 30 degrees to 0 degrees. Okay, so basically same step as before. First convert, so then let's see part I. First convert degrees into radians, so 30 degrees times pi over 180. That gives me 30 degrees in radians, which is pi over 6 radians. Now that I have this, I'm going to find average angular acceleration. So average angular acceleration from theta is equal to pi over 6 to theta is equal to 0. These are my bounds. So 0 minus pi over 6, and those become my bounds. So pi over 6, 0, and then same equation as before, 3 times 9.8 over 2 over 2, basically using the same equation right here, and then cosine of theta, d theta. Alright, this reduces down to, basically these are constant, and combined with this, those reduces down to negative 14.037, and integrating cosine of theta, I get sine of theta, and I have to plug these two in, so this is going to be equal to sine of 0 minus sine of pi over 6. So that is what this whole thing equals to. Now plug this into calculator, you're going to get 7.019 rads per second squared as your average angular acceleration from 30 degrees to 0 degrees. Okay, now that we have this, we're gonna have to find our angular velocity at pi over 6 or 30 degrees. So same thing, use energy. PE rod I is equal to PE. Now this time there is a PE rod at theta equals 30 because it's still in the air obviously, plus KE rod theta equals 30. So that's the statement. My PE rod initial is equal to 33.948 joules, my potential energy of rod when theta is equal to 30 is equal to m times g times h at 30 degrees and my KE of the rod at 30 degrees is 1/2 times the moment of inertia of the rod times omega at theta is equal to 30 degrees and squared. Okay, so height of the rod is equal to 1 meter times sine of theta, sine of 30 degrees, which is equal to 0.5 meters. Our moment of inertia of the rod, once again, is 1/3 ml squared. And so I'm gonna plug those in right now, as well as my numbers. Okay, so mass, first of all, 3.3948 joules is equal to 4 kilograms is our mass, G 9.8 meters per second squared. My H is 0.5 meters, and plus 1/2, 1/3, mass is 4 kilograms, length is 2 meters and squared, and then times let's just call this omega for now. Omega squared. Omega squared is what we're trying to find. Okay, so this is equal to 3.3948. This term right here reduces down to 19.6, and this term right here is 2.667 times omega at theta is equal to 30 degrees squared. Basically, I just wrote this as short, okay? I had no room. Okay, so to solve for omega at an angle 30 degrees, what you have to do is combine this to here and then divide by 2.667, then square root everything. So omega at 30 degrees is equal to square root of 33.948 minus 19.6 divided by 2.667 and then square root everything. So this gets me 2.32 radians per second as my angular velocity at 30 degrees. Okay, now that I have this, once again, I'm going to set up a similar expression to this before. So average acceleration, angular acceleration is equal to my final omega minus my omega at 30 degrees over time. I just found my average angular acceleration. It's right here. 7.019 rads per second squared. My omega final I found right here, 3.568. My omega at 30 degrees right here, 2.320, and over time. Alright, so times time over here and divide 7.019 to the side. So time is going to be equal to 3.568 minus 2.320 divided by 7.019. Plug this in your calculator, you get 0.178 seconds. So that is the time it takes for the rod to travel for the second half from 30 degrees to 0 degrees. Part I wants me to calculate the total change in angular momentum of the rod about the pivot from 60 degrees to 0 degrees. Okay, so the change in angular momentum is equal to the angular momentum final minus the angular momentum initial. Now the angular momentum final is equal to the moment inertia of the rod times omega final. Angular momentum initial is equal to moment inertia of the rod times omega initial. There is omega initial is 0, so this term cancels out. Moment inertia of the rod is 1/3 ml squared. So now I'm gonna plug in my numbers. So 1/3 mass is 4 kilograms, L is 2 meters squared, and then omega F is 3.568 rads per second. Plug this in your calculator, you get 19.029 units is kilograms times m squared divided by seconds.